Okay, so I just want to continue with what I was doing last time. Last time we'd started to look at, we'd looked at merge sort as an algorithm, and pretty much where we ended was saying that the algorithm was correct. And I guess very, very briefly, well, merge sort of a list of size n. We're going to do list L of size n. If that size is just 1, then we return L. Otherwise, we split L into L1 and L2, roughly the same size. Size L over 2 each. And then we merge sort L1, we merge sort L2, and then we run merge on those two ordered lists. So merge sort of L1 is an ordered list, merge sort of L2 is an ordered list. Then we merge those two ordered lists, and that's what we return. Okay, so that was merge sort. We also need to specify what merge is, and merge takes in two lists that are ordered, N1 and N2. I'm not going to write up again that they're ordered. That's we wrote that down last time, and I've said that a couple of times. So just remember, these two are ordered lists. And then what does it do? Well, if N1 or N2 is empty, then return, output the remainder of the other. Otherwise, successively, no, actually this is, yeah. Otherwise, compare the top, or first element of N1 with the first element of N2, and then remove and output the min in that compare, the minimum element of that compare. Last time I said successively do this, and then I threw it as an afterthought that you do this. But the way I'm writing it now, you're testing whether one of the two lists is empty, and then you're doing the comparison. So where do I want to put the logic of successively? Well, you want to be able to catch that in there as well. So I'm actually going to write this recursively. Then we're going to merge. When you remove, then you've updated either N1 or N2, right? So, well, maybe I'll say that explicitly. This updates N1 or N2. And then here I can have merge N1, N2. Okay, might look a little weird because here we have this procedure, merge N1, N2, recursively calling itself with exactly the same parameters, but they've been changed in here, right? Okay, so you're making progress because you're removing an element and going closer and closer to the point where one of the two lists is going to be empty. Okay, so this is just a slightly different way of expressing what the merge procedure was, but it's the same procedure. We just are expressing it now recursively. Okay, and then last time I gave a little example. Here was N1, and here was N2, and the actual example had numbers, and we output numbers, and so on. And I think I left with the question of what is the worst case number of comparisons that merge does with respect to what are we measuring? let's just say the number of elements. So the number of elements in N1 plus the number of elements in N2. And I think that's where we left last time. What's the worst case number of comparisons that this procedure merge does when you have two ordered lists that have these number of elements? And what's the answer? It's what? Half of that sum. Why?
Because when the two lists are equal in size, then basically you have the maximum number. When one of them is empty, then you just move the rest of the elements without comparing.
Well, okay, so the suggestion was that it's going to be half of this length because it sounded like you were giving me the best case, not the worst case. Another answer?
Just the number of items minus 1.
The number of items minus 1. Okay, a worst case. And so for worst case, you want to argue why it can never be more than that. Why would it never be more than that?
Because you can't, I guess, the number of comparisons you can do of n objects is n minus 1 anyway. So.
Number of comparisons of n objects is only n minus 1. Well, not if I compare every pair of them. That's n choose 2, which is n squared. So your answer is actually right, but your logic is, the logic at least you gave is not complete yet. Yeah?
Because when you only have one item remaining, you don't need to compare it to anything. So there's n objects, you compare all of them, and you have one remaining, and it just gets added on. So it's n minus 1.
Okay, what you said is correct, but not complete. Yeah?
Because every time you do a comparison, you get rid of an element.
Right.
And then when you get down to the last one, you don't compare it.
Yeah, okay. So what was said here combines some of the things that other people have said. Every time you do a comparison, okay, every comparison you do outputs something. It outputs the min, and it gets rid of something, okay? So when you do n, by the time you've done n minus, well, let's just say n first is an upper bound. If you did n comparisons, you'd certainly get rid of everything because there's only n things there, and every comparison outputs and removes something. But in fact, once you get down to, if you tried to get down to n comparisons, your last comparison involves an element in here and an element in there. And when you do that last comparison, you know what the order of the two are, so you can output 2 at a time. But actually, formally, you output 1, and one list is empty, and the other list still has one element. I guess I should have said it that way. When one list gets empty, the other list still has something in it, okay? Because in a comparison, you're only outputting one thing. It takes two things to compare, so you have something left in N1 and something left in N2, and you're looking at the last comparison. One thing gets output. There's still one thing left, at least one thing left in the other list. And therefore, here, you can output that last thing in the list that remains, which means you've only done n minus 1 comparisons. Okay, the key thing here is each compare removes one element. And that implies, at most, n compares. Okay? But if you look at the very last comparison, it has to involve something from N1 and something from N2. It's the very last comparison. There's going to be a last comparison. At that point, you have, when you do the last comparison, one list becomes empty and the other list still has one thing in it. Okay? So you haven't output n things yet. You've only output n minus 1 things. When that list becomes empty, and then according to this, you can output the remainder of that list for free. N minus 1 compares. And I'm not going to write out all those little words that go there. Okay? Okay, so that's the worst case. Well, actually, that says that the worst case number of comparisons is at most n comparisons. Okay, is the worst case actually that much, n minus 1? What am I really asking when I ask that is there a case, can you think of lists, 2 lists, where the number of comparisons is actually as big as n minus 1?
Yeah, just evens and odds.
Yeah, just evens and odds, for example. Just where they interleave, you take one from here and take one from here and take one from here and so on. Okay, and you can think of other lists as well that would do n minus 1 compares. So the worst case number of comparisons is, in fact, exactly equal to n minus 1. Okay, so we've got that. Now I want to analyze the time for the whole merge sort algorithm. And we already did correctness. Essentially, last time we argued that this algorithm is correct, this algorithm is correct, that algorithm is correct. Okay, so let T of n denote the worst case number of comparisons done by merge sort on a list L of size n. Now these things, by the way, these stripes here, that's the official frame. I don't know how many people can see it, but this is where the board actually ends right here. And the frames, at the very beginning, if anybody had seen me measuring with the eraser, these frames aren't the same. I'm just saying that for the people in the booth back there. This is a smaller frame than this one, so, but yet the boards are all the same. So I don't know why they didn't use the boards as the frame and not the stripes. But okay, so if you see me going over this line, thinking that this is the right frame, tell me to stop, because otherwise it won't. The picture won't be in frame. Okay. So let T of n denote the worst case number of comparisons done by merge sort. That means that algorithm, the recursive algorithm over here, which as part of it calls this recursive algorithm. T of n is the worst case number of compares done by merge sort on a list L of size n. And we want to find a function that either captures this exactly. And remember the picture we started with in the beginning of the class? WAN. We'd like to know what that is exactly. Okay. What's A in this case? Yeah, A represents the merge sort algorithm. Okay. We'd like to know that exactly. And actually here we just said that's T of n. But more abstractly it was WAN. But this is for merge sort. That would be for merge sort and so on. We'd like to know that. But as I mentioned, it's generally difficult to get that function exactly. So we're going to look for some upper bound, something like that. We would like to prove that T of n is big O of some function like that. So we're going to try to get a function f such that the true worst case number of operations that merge sort does is upper bounded by some function f of n that we can actually characterize. Does anybody know what f we're going to get?
N log n.
N log n is a good guess. Okay. All right. Well, let's actually do it. So the way we're going to do this is to set up a recurrence relation, or a recurrence, for T of n. And we're going to set up that recurrence by mirroring the recursive structure of merge sort. So generally speaking, whenever you have a recursive algorithm of this type, or a divide and conquer kind of algorithm, you can set up a recurrence which expresses what the worst case number of operations is by just mirroring or representing the recursive structure of the algorithm. So divide and conquer kind of algorithms are relatively straightforward to analyze what their worst case running time is. So T of n equals, well, I said we have to, in order to set up the recurrence relation, we have to mirror the recursive structure of the program, or of the algorithm. By the way, I'm assuming everybody knows what a recurrence relation is. A recurrence relation is just a function which is defined in terms of itself. Now, you want it defined in terms of itself with smaller parameters, otherwise that recurrence relation, when you try to calculate with it or when you try to solve for a closed formula, you're not going to make any progress. But what it means is we're looking for T of n, and it's going to be expressed in terms of T of some other parameter instead of n. Okay? So we find the particular recurrence relation that we want by looking at the recursive structure of the algorithm. So T of n, represents the worst case number of operations done when you input a list of size n. And what happens here, you split into two lists. And remember last time I said split arbitrarily into two lists roughly of the same size. Well, depending on your representation of the list, that could take one operation, just if you're keeping pointers to where the list boundaries are. Or if you were going to replicate the list, that would take time proportional to the length of the list. So we could, either way, we could count, let's say, n operations, but those aren't comparisons. Okay? And remember, I said last time that comparisons are the primitive operations, and we said to be a primitive operation, the number of those primitive operations has got to be proportional to the total number of operations in the algorithm. Otherwise, it's not fair just to focus in on the primitives. So I'm telling you a little bit about what are the non-primitives here. You have to split up this list. Well, it's either one operation, so certainly the number of comparisons is going to dominate that. Or even if you replicated the lists, you copied them somewhere, it's just n operations, where n is the length of L. And we'll see that when we count comparisons, that's going to be bigger than n anyway. And so all of this is sort of to justify that just counting comparisons, that's proper in terms of calling comparisons the primitive operation. Okay, so T of n, number of operations or number of comparisons, focusing on the primitive operations, number of comparisons we do on a list of, Mergesort does on a list of size n. Well, down here we're going to merge sort of L1 and merge sort of L2. Okay? So this has to be translated into T somehow. And let me just show you what it is. You have two merge sorts there. One is of L1, one is of L2. How many comparisons does each one take? How many comparisons are done when you merge sort a list, merge sort L1? Worst case number of comparisons done is what? T of L over 2. Right. Yeah. The way I want to actually do it is another step. The first step is, I asked the question, what is the worst case number of comparisons that are done when you merge sort a list L1, which is of size roughly n over 2? And the first answer is, I don't know. Okay? It has no more immediate answer than my initial question of what's the worst case number of comparisons done when merge sort takes a list of size n. We don't know what it is, that's what we're trying to find out. But you can express what it is. We have notation to say what it is. And exactly right, what was suggested here, it's T of n over 2. Okay? The worst case number of comparisons to sort L1, list L1, is T of n over 2. I don't know what that is, but I know how to express it. And since we're doing both L1 and L2, then I have the 2 out here. Okay? So you do that, recursively. So the recurrence relation is mirroring the recursion in the algorithm. And then you have to merge. You have to merge these two-ordered lists. Okay? That takes comparisons too. Or that's actually the only place where we're doing real comparisons. This was just setting up the next level of the recursion. But now we have to say, how many actual comparisons, and what's the worst case number of comparisons that are done when you take in two lists, when you merge two lists of size n over 2? Is what? N minus 1. That's exactly what we were discussing earlier. Okay, n minus 1. So this is the body of the recurrence. Okay, the main part of the recursion or the recurrence that's expressing what t of n is. But we also need a base case. As n gets smaller and smaller, ultimately we get down to small enough size n where we actually know how many comparisons are done. So looking here, there are different ways you can set up the base case, but looking in here, we said if the length of the list is 1, then we return. How many comparisons does that involve? 0. Yeah. So we could say t of 1 equals 0. Okay? And you could put in other base cases. Just usually the base case is you get down to some small number, so some small size of the problem where you actually can you know how many operations are done, and you just put that in as your base case. Maybe it's t of 2 or t of 5, or actually what's t of 2? It's 1, yeah. I mean, it could be that you have one list of size 2 and one list of size 0, okay, in which case it's 0 operations. But worst case is you have one list of size 1 and another list of size 1, in which case the t of 2 is equal to 1. So we could have had that as a base case too. But let's just look at these two. So now I want to, now we have a recurrence relation for t of n. What can you do with this?
For all n's.
It's what?
Write it for all n's and then add it up.
Okay, I think you're hinting at how we are going to get a closed form solution, which is a good first thing. But I want to point out something else, which is not in this class, but frequently in science, anywhere in mathematics that uses recurrence relations, which is very, very common. Often they can't go much beyond the setting up of the recurrence relation. But what you can do with this is that you can program it into a program and compute actual values. So if I take n, let me take it as a power of 2 here, just for convenience. Let's say I take n equal to 1024. Okay, I can use this recurrence relation to ultimately figure out what t of 1024 is, because t of 1024 is twice t of what's half 1024? 512. Thank you. It's twice t of 512 plus 1023. Okay? Well, then I need to know what t of 512 is. Okay? I don't know, but I do know I have this recurrence relation, so I can say t of 512 is equal to 2 times t of 256 plus then, whatever the 511 should be here, except I've got 2 of those. Anyway, you can just, if you write up a program that incorporates this, and then call that program of t on some specific number, that program will calculate it. Okay? And a lot of times in various parts of science, you can set up a recurrence relation, and then you can use the computer to actually find what the numbers are and come out with a table or a plot or something like that. But a better approach, if you can do it, and in this class we will be able to do it on recurrence relations that we're looking at, a better thing is to solve for t of n, or solve for a closed form solution to t of n. And what that means to solve for a closed form solution is that we're going to be able to express t of n as a function of n, but it won't involve t anymore. Here's a function of n. T of n is this function of n, but it's got a t in it. So it's a recurrence relation. It's defined recursively. Ultimately, you'd like to be able to say t of n is a function of n without having to put the t in there. So it'll be some functions that you're familiar with. Maybe it's an n squared, maybe it's a log, whatever. But it'll look like a normal kind of function without having t on the right-hand side. Just t is on the left-hand side. So we want to solve for that. Okay, how do you solve recurrence relations? How many people have seen that in some prior math course? There's a hand back there. Okay, one hand? Only one person's ever seen how to solve a recurrence relation. Okay, two hands. Okay, good. Can I see 3, 4, 5, 6? Anybody? Okay. Sold at 10. All right. Okay, so we'll solve this one, and then we'll do a little more complicated one, and then I'll sort of tell you how we can solve them for the kinds of recurrence relations we see in this class. But sort of the meta answer is that there are whole books full of techniques for solving recurrence relations, and mathematicians have all kinds of general techniques. But we're going to look at some very specialized techniques that are appropriate for the kinds of recurrence relations we'll see in this class. Okay, so the most useful kind of approach, I'm going to erase the algorithm now because we have the recurrence relation for its running time. We don't need the details of the algorithm anymore. The most basic approach, and one that involves learning something that you can keep with you for a while, is unwrap. So you unwrap for a while, then you see the pattern. Sometimes that's called guessing the pattern, but better if you see it. See the pattern, then you solve for some summation expression. This just usually involves algebra or remembering geometric series or whatever sums from high school. And then that's about it, and then clean up. Or you could see the pattern, do some guessing at this point, and then prove the pattern is correct, is actually the right pattern by induction. Sometimes you want to do that. Okay, let's do this, make this concrete. We'll look at that recurrence relation and solve it. So when you unwrap, what it means to unwrap is you use the recurrence relation on some specific value of n for a little while until you see what's actually going on in successive unwrapping or successive uses of the recurrence. And it's very useful to start with a number that's going to make the unwrapping simple. Okay, now this is just a matter of experience to some extent. N here is being divided by 2 each time. We also have a multiplicity of 2. That may be confusing the next point I'm going to make. But n divided by 2 here suggests that a good value for n to make things sort of natural is going to be a power of 2. If I make n something that's not a power of 2, I'm going to start getting weird numbers and unhelpful in order to see the pattern. So I'm going to start with a value that's a power of 2, maybe let's say 16. Okay? So I want to know what t of 16 is. Okay? Well, I don't know what t of 16 is. Okay? But I have that recurrence relation over there, which tells me that t of 16 is twice t of 8. Okay, so I can draw a tree like this, t of 8, plus n minus 1, which in this case is 15. Okay, so I'm going to do something else that slightly simplifies things, and it's also just a matter of experience and judgment whether you can get away with this. This was a minus 1, which means this is actually smaller than if I have 2t of n plus n. And so now we have to say this. Okay, so t of n is less than or equal to that. And let me just call that f of n. Okay, so definitely t of n is less than or equal to that because there used to be a minus 1 there, right? So if I throw away the minus 1, I can call it something else, f of n, and t of n is less than or equal to that. So what I'm actually going to derive is what f of n is. So f of 16 everybody understand if I get a closed formula solution for f, I have an upper bound on t. Okay? And again, it's a matter of judgment of whether that's going to be useful or not. I mean, it is mathematically legitimate for me to erase everything and say f of n is 0. Okay? No. What was I talking about? F of n gets big. Okay. Forget that comment. Anyway, it's just a matter of judgment of what you can simplify and still get an answer that's meaningful. Throwing away a minus 1 is small change, and as long as we remember which side we're erring on, that we get Tn less than or equal to Fn, and now we characterize Fn, we still have a legitimate result for T. Okay, so F16 is twice f of 8 plus what? 16. So it's going to be my sum column, 16. So all I know about F16 is that it's twice f of 8 plus 16. Now, what do I know about f of 8? Yeah, it's twice f of 4. Okay, plus, so I'm talking about f of 8 is twice f of 4 plus what? Plus 8. Okay, but here's f of 8 once, and here's f of 8 again, so it's 2 times 8 in terms of the sum that's happening. Okay, f4, f4. Well, what's f4? It's what? 2f2, but first you have to say, I don't know. Okay, to remind yourself, you're not getting the full, you're not going to the complete answer, you're just taking one step of the recursion. Okay? So this is f of 2, twice f of 2, but according to the recurrence, you have to leave behind 4. You have to add 4 to your sum. And we have 4 of these, so I'm not going to draw out everything again, but remember that it is there. But we're adding now 4 times 4. Okay? And what's f of 2? It's, I don't know, but it's twice f of 1. F of 1, f of 1, okay, plus 2. The 2 is being left behind. And we have 1, 2, 3, 4, 5, 6, 7, 8 of those. So we have 8 times 2. Okay? And then what's f of 1? It's 0, according to the recurrence over there, the base case. So these are just zeros, so obviously here, f of 1 is, just 0. So nothing is left behind here, and we get a 0. Okay, so what is f of 16? It's 16 plus 2 times 8 plus 4 times 4 plus 8 times 2, which is equal to 4 times 16. There's 4 of them, and each level adds up to 16. So 4 times 16, is that 64? Okay, So we now know that F16 is 64. So what is T16? It's less than or equal to 64. Actually, we can say it's strictly less than 64. And if you had wanted to do this exactly for T, then here you would have left behind 15, and here it would have been probably, what is it, 2 times 7? I don't know. But we'll see that this is adequate in a moment. Okay, so we've done this unwrapping for a specific value of n. Well, the general paradigm here is unwrap, see the pattern. So seeing the pattern means expressing what's going on here in terms of n, not in terms of 16. Okay? So this is f of n. Now you're thinking about f of n. And so what's being left behind? If we're thinking of n abstractly, what's left behind? It's just n initially. Okay? And then at the next level, 2 times 8. But what's really happening in terms of n is you have 2 times n over 2. Okay? So 2 times n over 2, which is also equal to n. In the next level, you have 4 times n over 4. Okay? But let me try to write that. Again, you want to get to the pattern, so you want to start seeing this more generally, more abstractly. So if I have a level I, call this level 0, call this level 1, level 2, level 3, okay? Then the next, well, to see this abstractly, this is 2 to the I times n. Okay, but I is 0 at this point. 2 to the 0 is 0. Here, you actually, no, I want to n over, yeah, it's also 2 to the I, right. Okay. They just cancel, but all right. Maybe I didn't need this level of abstraction yet. Okay, and in general, well, in general, for any level I, what you're getting is 2 to the I times n over 2 to the I. And here, I was 2, so 2 squared is 4, n divided by 4, and that's, again, n. Seeing it cancel. All right, so the total is always n times the number of levels. Right? Stop me if you're not seeing it. You have a furrowed brow. Does that mean you have a question? Or both of you, actually, right? An arrow. Yeah.
For the total, I mean, I'll just have to see you do that.
Okay. But actually, I was actually pointing behind you, too. Question?
I'll wait.
Okay. So what I'm saying is we're seeing the pattern that every level, what we're adding up from applying the recurrence is n. Okay? And therefore, the total can just be expressed as the number of levels in this unwrapping times n. Now, when n was 16, the number of levels was, well, we said level 0 through level 3. That means there are 4 levels. Okay? What's the relationship of 4 to 16? Well, there are lots of them. 2 to the 4 equals 16. Okay? So the total, T of n, is equal to n times the number of levels in the unwrapping. Okay? And how many levels do we have? Well, what we know about the number of levels is that, what did you say again? 2 to the number of levels. Are you stretching or you're answering? Is that a stretch or an answer? Oh, okay. 2 to the number of levels equals n. Okay? So we started out with n, and we divide by 2 and divide by 2 again and divide by 2 again until we get down to 1. So we know that 2 to the number of levels is equal to n. So what's the number of levels? What function connects these two facts, or this fact? Log base 2, right. You take the log base 2 of this side and the log base 2 of that side, and you get the number of levels. So you can think about the log base 2 as of n. It's the number of times you divide by 2, starting at n, until you get down to 1 or below. Depends on whether n is a power of 2 or not. And that's basically what the log, at least the discrete, the rounded log, the log base 2 of n is. It's the number of times you would divide by 2 to get down to 1, if n is a power of 2. So we're seeing it precisely this way. So what is the total? T of n is equal to n times the number of levels f of n. We've been solving for f, right? F of n is equal to n times log base 2 of n. Okay? Now we said t of n is less than or equal to that. T of n is less than or equal to f, so t of n is less than or equal to n log n. So t of n is equal to big O of n log n. And we have the result that we wanted, and that somebody had said initially, that the worst case number of comparisons in Mergesort is bounded, big O, bounded by n log n. Yeah?
What happened to the base 2 for the log? When you went over to FO n log n?
Okay, yeah, very good question, because this is going to happen a lot. So I said n times log base 2 of n, and that implies t of n is big O of n log n. Okay, so what happened is that the big O ate it. Bases of logarithms don't matter in big O notation. So why is that? What's the relationship of numbers, well, log base A of n, how does that relate to log base B of n? Where A and B are two different bases. Something like that. Okay. And I'll generalize that in a minute. But anybody else know the answer? I hear derivative in there somewhere. Who said that? Oh, way back there. I heard derivative, but I don't think that's related. No, this is something you learned in high school. If you're like me, you forgot it until I had to teach it one day, and then I remembered it. But that was a while ago for the first time. No, the log with one base is equal to a constant that depends on AB. It's just some constant number depending on AB times the log of B. So logs of different bases only differ by some constant of proportionality. Okay? Now, you remembered, a minute ago, you suggested what the actual constant is. And what is it? Or what? Log what?
Log A, B, base A.
Okay, so the suggestion is that this is log base B of A, log base B of n. So everybody should go home and think about it. Don't go home now, but when you go home, you should look this up or think about it. If we spent the time, we could derive what the right constant is. But my point is that logs of two different bases differ only by some constant factor, multiplicative factor. Given b and a, this log base b of a is a specific number. B and a are specific numbers. This is some specific number. So they just differ by proportionality. Okay? So getting back to the question of what happened to the log base, what happened to the 2 here? Okay? Big O, so I could have just put the 2 in here too if I wanted to, but the point is that whatever the base of this log is that I want to use, maybe I want to use log base e or log base 10 or whatever, how does it relate to log base 2? This is the actual correct sum, n times log base 2 of n. But if I wanted to express that as log base 10, it's n times log base 10 of n times some constant, which what I said over here is just now determined by 2 and 10. It's some constant number. And what happens when you look at big O of a constant times n times log base 10 of n? No. When you look at that, that's big O of n. The constant disappears, log base 10 of n. Okay? Take the ratio of these two functions, and because it's a constant, then we see that this big O relationship is valid. And because this is true for any base I wanted to pick, in the end we just don't even bother expressing the particular base. So this is a sloppy shorthand. Not having a base there is a legitimate, but maybe sloppy shorthand saying we don't care what the base is. Whatever base you want to put in there for convenience, this would be true, that this function is big O of that, because that base would only differ by a constant which gets eaten up by the big O anyway. So you don't really need to put a specific base there. Whatever base you would use, you would be right. Okay. All right. So that is an example of how you unwrap. You see the pattern in terms of n. You solve. Our solving was particularly simple in this case because every level left behind n. So our solving of the sum was particularly simple. It was just n times the number of levels. Okay? In general, the solving part can be more difficult. The summing part, sorry. The summing part can be more difficult where you have to use more arithmetic. Okay? And let me just begin an example that I'll do in detail next time. And by the way, there are two handouts on the class website that I put up there from the first day that talk about solving recurrence relations. And so you can look at those. I think they do the Mergesort that I just did, and definitely do the next example that's technically more difficult, but illustrates that the summing is. So let me just put this up and ask you to do one thing before next time, which of course only a few people will do, I know from experience, but okay, so t of n now is 4 times t of n over 3 plus n over 2. I don't know an algorithm that mirrors this. This is just an exercise in solving a recurrence relation. And we want to use the approach that's there of unwrapping and trying to see the pattern. So what you can do is take a number, and it should be a power of 3. It's because we're dividing by 3 here. Power of 3 is a good choice, like 27, right? And unwrap it. Take a piece of paper, do this unwrapping tree, and then try to see the pattern. And so next time we'll be able to set up that and see the pattern quickly, and then focus on doing the summation, because the summation is a little bit more involved than this example was.